So this is Donna Nelson with the second organic chemistry lecture on aldehydes and ketones. And now we're going to discuss the nucleophilic attack at carbonyls under acidic conditions. These are instances in which the nucleophile is not a strong enough nucleophile to be able to react with the carbonyl, the aldehyde or ketone, without being catalyzed by a little bit of acid. Usually that's what's used, it's just a small amount of acid. And so here we are, we're going to look at the reactions with oxygen nucleophiles and nitrogen nucleophiles. And then in the next lecture, we'll go on to hydrolysis of acetals, amines, and enamines, sulfur nucleophiles, and hydrogen nucleophiles. Except, I might mention that I have moved the hydrolysis of acetals up to accompany the oxygen nucleophiles because acetals are formed by the reactions of oxygen nucleophiles with carbonyls, and it makes more sense to cover them this hydrolysis of acetals in here, right in between section 19.5 and 19.6. So let's start looking at the actual reactions. So this is a situation in which you have a nucleophile that is not going to be strongly enough reacting to be able to just simply react with the carbonyl without having the carbonyl polarized by a small amount of acid. So the nucleophile over here, NuC minus, is equivalent to A minus here. So this, you have the acid, so A is going to be the conjugate base, and that becomes the nucleophile. So this is simply a situation in which A minus is not a strong enough nucleophile to react on its own with the carbonyl, and so the carbonyl is not reactive enough, and so it's given a little boost by attaching a proton to it, and initially the carbonyl is polarized a little bit, and when the H plus is attached to the oxygen, it becomes more polarized and therefore more reactive. And so the first step here is the proton transfer to the carbonyl, the pair of electrons. One pair of electrons on oxygen attacks the proton, displacing A minus. And so now the conjugate base becomes the nucleophile. And you can see the carbonyl is polarized. There is a much greater charge borne on oxygen. So having this proton up here pulls more electron density off of this carbon, making it more attractive to the anion. And so you have the anion do the attack at carbon, which is partially positively charged. A pair of electrons, the pi electrons, move out onto oxygen, neutralizing the positive charge on oxygen, and now this becomes an alcohol functionality, hydroxyl. So this is what needs to be done when you have a weak nucleophile. Acidic conditions are required in order to have a weak nucleophile attack the carbonyl carbon, as I just discussed. When a nucleophile attacks the carbonyl carbon, the equilibrium depends on the ability of that nucleophile. So here this is going to be chloride to function as a leaving group. If it can function as a leaving group, then you're going to have the reactants favored at equilibrium, because you know that you're not going to have the hydroxyl group depart, this reaction will not go further. And so here, because chloride is a good enough leaving group, the reactants are favored at equilibrium. This is an organization, a table of the different nucleophiles that we're going to cover. They're not really listed exactly in the same order that we're going to cover them. First, we're going to cover the oxygen nucleophiles, then the nitrogen nucleophiles. The sulfur nucleophiles are going to be down in here in the next lecture, but it is useful to have the sulfur nucleophiles listed next to the oxygen nucleophiles so you can see the similarities. Remember that sulfur falls just below oxygen in the periodic table, and so a lot of the reactions are very similar. Here, notice that you have two pairs, two non-bonding pairs, two non-bonding pairs, one non-bonding pair. Here you don't have any non-bonding pairs, but H- is furnished as a nucleophile, and in these cases, the nucleophile is anionic carbon bearing a negative charge. And so even though the carbon-magnesium bond here does have some covalent character, you can, when drawing the mechanisms and thinking about the reactions, you can think of this carbon as being an anion and bearing a negative charge. You can draw the mechanism that way, and you won't go wrong. It's okay. It's suitable to think of this as an anion, although it's not really a fully ionic bond. It's somewhere between covalent and ionic up here in this Grignard. So let's look at the reactions. Remember, I pointed out the non-bonding pairs, and that's going to be what does the attack on the carbonyl in each case. So here we have carbonyl in the presence of water with a non-bonding pair of electrons, remember. And so when these two are in the presence of each other, this oxygen can attack at the carbonyl carbon and you can form a hydrate. Although the equilibrium usually doesn't favor the hydrate, but it can be attained. It's good to keep in mind that it can be attained. In some cases, it can become an important side reaction or an important part of the mechanism that you must go through to get to the product. So, under basic conditions, OH itself is the nucleophile. A pair of electrons on oxygen doesn't attack at the carbonyl carbon. The pair of electrons in the pi bond move out onto oxygen, generating a negative charge here. Now you have formed two CO bonds, and the negative charge on oxygen simply picks up a proton, one of the non-bonding pairs on this negatively charged oxygen, picks up a proton, and the pair of electrons in the OH bond moves on to oxygen, regenerating hydroxide. And so this is how the hydrate is formed from the carbonyl. This is the mechanism under the base catalyzed hydration. Just a small amount of base is all that's needed because you can see it is a catalyst. Under acidic conditions, you have the carbonyl, which is protonated by the water, which is bearing a proton. A pair of electrons, a non-bonding pair on oxygen, picks up a proton from the water, and so now this generates the neutral H2O. And so you have the protonated carbonyl compound. Now you have The second CO bond is formed when the pair of electrons on oxygen comes in and does an attack, and it will come up here. It won't come in from the side like that. It will come up and occupy, the pair of electrons will come up and occupy the the anti-bonding orbital of the pi bond, assisting in the cleavage of the pi bond here. So it doesn't come in from the side, it comes in from the bottom. And so the nucleophilic attack, that is. And when that happens, the pair of pi electrons moves out onto oxygen, satisfying the positive charge. Now you have two CO bonds, and so when you simply have a pair of electrons on oxygen deprotonate the oxonium ion, the pair of electrons in the OH bond moves back onto oxygen, satisfying the positive charge and generating the hydrate, and also generating the hydronium ion, regenerating that. So again, this is a catalyzed reaction. This is just a catalyst, and it's regenerated. When you're drawing mechanisms, under acidic condition, a mechanism will only be reasonable if it avoids the use of formation of strong bases. So you will not have the presence of bases under acidic conditions. So you will not have, the key word there is strong base. You will not have anions present under acidic conditions. And you won't have a strong base generated. If it's part of a leading group, it will be protonated before it comes off. And correspondingly, under basic conditions, you won't have a strong acid formed because it will be deprotonated. And so you have to keep things like that in mind. So here's examples. And you saw how we could form hydrates earlier using the same mechanisms. Instead of using water, you simply use an alcohol here. And so instead of attaching an OH group, you will attach OR using the same type of mechanism. And so this is called an acetal. So this corresponds to the hydrate where you had OH, OH, now you have OR, OR. This is an acetal. Under acidic conditions, one equivalent of ketone or aldehyde reacts with two equivalents of alcohol to form the acetal. That's because you're having to attach two alkoxy groups to each carbon of the carbonyl. Commonly used acid catalysts are para-toluene sulfonic acid or tosyl acid or sulfuric acid. So now let's look at the mechanism here. So the first few steps will be analogous to the steps that led to your hydrate that we saw a couple of slides ago. So the first step is simply protonation, and then you have attack at, through the anti-bonding orbital, the attack of oxygen using a non-bonding pair, which will come up and occupy the anti-bonding orbital down here. And then that helps the pi bond break. The pair of electrons moves out, satisfying the positive charge on oxygen, and you have formed this new single bond, carbon-oxygen single bond. The oxygen is bearing a proton and a positive charge. Your conjugate base will pluck off the proton, the pair of electrons moves back onto oxygen, giving you the hemiacetal. Think of hemi as half, acetal, here's the acetal, so you're halfway to the acetal here. So now you need to replace this hydroxyl with that alkoxy. And so the first step is to protonate this group. This is the one that you're wanting to remove, that must be removed. So what you're doing here is you're drawing a mechanism that will show this hydroxyl group being replaced by an alkoxy group. Now, actually, in real life, all possible functional groups that can be protonated will be protonated under this condition. It's just that they won't lead to any reaction occurring. So the protons are constantly involved in equilibria in which they're coming on and going off of the different functional groups that can bear protons. It's just that when this one picks up a proton, it can go on to a reaction. If you protonate this, nothing will happen except you'll go back to the reactants. And you're not interested in that. You're interested in going on down this way. So you just draw the mechanistic steps that you're interested in this case. And here what we're interested in is showing the steps that go on to the product. So the first step is going to be protonation of this group that we want to be our leaving group. And so it has become a nice neutral leaving group. This will depart as neutral water, H2O. And so then you use a non-bonding pair on this oxygen to form a double bond, and water will depart. And now you have this oxygen, which instead of being protonated, you have this alkyl group. You are very used to seeing protonated carbonyls, but this is just as stable and just as likely to form. You have an alkyl group attached to the oxygen. Oxygen is bearing a positive charge. This carbonyl will be polarized. The pair of electrons in oxygen comes in not from the side, it will come in from the bottom, occupying the antibonding orbital and helping that pi bond cleave. And so the pair of electrons in the pi bond moves out onto oxygen, satisfying the positive charge and forming your new CO bond here. This is the new CO bond, which is, this has been sort of twisted, turned around. So this group is this group. Instead of going up, it's going out to the side. And so now you have this alkoxy group, which is protonated. And so the final step is simply to deprotonate using the conjugate base of the acid that you started with. And so it takes all these mechanistic steps to go from the carbonyl to the acetal. Notice that each one is reversible. Each one is reversible. And notice here, water is given off at this step, and so you can push this towards completion by removing water, or you can push it back towards the reactants by adding water. So acetal formation is an equilibrating process. So usually the acetal is favored at equilibrium, and for most ketones it is not favored. This is simply steric. We've got steric effects here. And notice this is reversible, as I said. If a diol is used, then both equivalents of the alcohol can come from the same molecule. And so you've got this cyclic acetal that is formed. And so this can be formed as a protecting group for the carbonyl, because this will not undergo all of the same reactions that a carbonyl will undergo. And so if you're wanting to keep the carbonyl while you do some other reactions at a remote part of the molecule, you can protect the carbonyl by using this cyclic acetal. Acetal formation is reversible, so you can drive the equilibrium towards the products by removing water, or you can drive it towards the reactants by adding water, and so this can be put on as a protecting group and then removed. The protecting group can be removed. Acetals are hydrolyzed with aqueous acid to yield the ketone or the aldehyde and two equivalents of the alcohol. Acetals will only react with water under acidic conditions. So under basic conditions, there's no reaction. So here is the mechanism, hydrolysis of acetals. Actually, this is just the reverse of what we saw earlier. I can go through it. So the first step is protonating the alkoxy group, protonating the oxygen. Now you have the nice neutral leaving group, the oxonium ion. A pair of electrons on oxygen can move in, form a double bond here, and you have the alcohol leave. So you lose your first molecule of alcohol. Then you have water come in, occupy the anti-bonding orbital, a pair of electrons on oxygen, and the pair of electrons in the pi bond moves out onto oxygen, satisfying the positive charge. Then the proton is removed using water, and so if you have an excess of water, this is all going to be driven towards completion. Now, this is your hemiacetal. Your hydronium ion furnishes a proton, which becomes attached to the oxygen of the alkoxy group, and a pair of electrons on oxygen picks up the proton, the pair of electrons in the OH bond moves onto oxygen, giving you the stable water. Here, this is going to be a neutral leaving group. This will leave as the alcohol. The pair of electrons on oxygen moves in to form the carbon-oxygen double bond. This gives you the pi bond. A pair of electrons in the CO bond moves out onto oxygen, satisfying the positive charge. And so now what you've done is you've generated the carbonyl, which is protonated, and so now you simply have the water come in and deprotonate this oxonium ion, and this has generated the ketone. So let's look at how this synthesis could be accomplished. Convert the ester to a primary alcohol, which requires LAH, leaving the ketone unchanged. LAH would reduce the ketone as well. So you'll use the acetal as a protecting group for the ketone, and then you can reduce this ester to the alcohol. And so you can practice with that. Here, now we see formation of the acetal, and then reduce the ester. The acetal will be left. And so then, after it is reduced, then you remove the acetal, functional protecting group, by just using some dilute acid. So the hemiacetal is difficult to isolate. You may never see it. You may only see the carbonyl and the acetal. This is favored by removing the water. So you can drive the equilibrium to the right by adding an excess of water, or you can remove the water and drive the equilibrium to the left. So this is a cyclic hemiacetal. It's possible to form this when the compound contains both the carbonyl group and the hydroxyl group. So this, when it comes back and forms the acetal, you're going to form a ring. And cyclic hemiacetals are important in carbohydrate chemistry. So this can form this oxygen, and that carbonyl can form the hemiacetal ring. So this finishes oxygen nucleophiles, and so in the next lecture, we will look at nitrogen nucleophiles.